Oops. So the aim of neurofeedback training is it's a calculation of the alpha bandwidth over beta, which is the beta is associated with the alertness, and the alpha is associated to relaxation. So when your relaxed mind is higher than your concentrated mind, alpha goes up. And so this is calculating, so she's putting the sensor, she's scanning for sensor, and now she's gonna look if she has a good signal. You see on the bottom here you have the FFT of the signal with different colors, which are different bandwidths. On the bottom right is the raw data, and on the top you see alpha over beta. And the aim of the training here is to increase this alpha over beta ratio. Now she has her eyes open, but the alpha is going to go up as soon as she closes her eyes, and the more she relaxes, the more it should go up. And the feedback, well, we don't have sound. Don't know if you hear. It's just a water white noise that just increases in volume. So you're concentrating, well, you're relaxing, and you're trying to focus on the sound that you hear and try to make it louder and louder and louder. Or if you look at it from another point of view, it's a bit like a mirror. If you hear it go louder, it's telling you you're doing good. And so it goes and it follows this ratio. So the more you train, the more you're able to pretty quickly enter a relaxed mode, and this increases and improves, and this has benefits also on how to cope with stress if you train your alpha brain. So I think you get the picture. There is also, if I have time, I'll show you, we developed a biofeedback with the heart sensor, and so it's also to enhance the relaxed state, or to relax. And this is really with breathing. Like, she was also closing her eyes and really concentrated on her breathing and trying to make the sound louder. With the heart rate, it's the same, but you have eyes open, and so you have a visual feedback. 2 minutes, okay. Due to frequent updates of the firmware, it was necessary to have a firmware update over RF. It's infrequent, but it's very useful. So you mainly do as like we just saw, so you scan the sensor and you select and request a firmware update. The home PC checks battery levels and then performs update and resets the sensor. The largest power consumption occurs during the time that the radio is switched on. So for power energy savings, this was crucial. So reception takes twice as much as transmission. So the sensor listens for home PC to broadcast only 15 milliseconds every 15 seconds. And when the sensor hears a broadcast, it fully activates the radio and it begins the session by passing attributes to the home PC so that the PC can list the sensor for the user to select. The sensor, however, will switch off the radio after 1 minute of inactivity from the home PC in order to conserve power. Each sensor has a unique address, and once a sensor is activated or has completed the download, it goes back to radio silence mode. Data download. The home PC is in full control, instructing sensor to send across data. And this is also for energy saving. It simplifies the protocols for multiple requests during packet loss, and if the PC detects battery low. Streaming to save power sensor. The to save power sensor always transmits and never listens. Lost packets are considered inevitable, but PC should interpolate data. In this case, the PC is doing the computing. Firmware updates. This is a key issue here, since since firmware updating is so important in any wireless system, then the radio communication protocol should insist to be part of this issue. In our case, a very simple but effective low-power methodology is being used. Major savings are achieved by understanding the use case and then adapting the radio protocol around the use case. Switching the radio off for as long as possible achieves the simplest savings, but impacts user experience. If you have to wait 1 minute every time you try to find a sensor, you're going to abandon. By sending heavily processed data, energy savings are achieved due to much lower number of bytes transferred. So the sensor is processing a lot of data. But there's a maximum that you can do because it also uses a lot of energy. And data loss and retries to repair data loss uses energy. As far as possible, we try to timestamp data so that lost packets are interpolated. We do apply retires, but this is strictly limited. And frequency hopping and switching the receiver on and off, resetting the radio each time to save power, or frequency hop may achieve energy savings and improve tolerance to packet loss. However, switching takes time and energy in itself, and so we chose against this frequent resetting of the radio parameters. Users, that's Denni Majoe's humor. Users are bad boys and girls. They damage the sensors with force of a gorilla. They don't obey instructions. They switch the sensors off instead of on. They switch the sensors on instead of off. They walk away during a session and break the radio link, etc., etc. The key point is that no matter what the use case analysis, the users will always downgrade their energy budget from a calculated one, which means you can aim to something, but you have to take in consideration that the usage is going to be something else. Repeated battery recharge weakens the battery performance, so naturally the energy efficiency drops with usage. But we saw the result is several hundreds of megabytes of data gathered from 130 plus users over several months, and most 90% users happy with the sensors for wearability and ease of use. Sensors in the main achieved the energy savings and reliability, though there were many breakage and battery weakening issues. No data privacy issues, even when used in dormitory environments, but there was heavy data corruption occurred in areas where there was multiple Wi-Fi. I have a few minutes, 1 minute. And so at the time of the beginning of Optimi, there was the low energy Bluetooth 4 was not available. Now we find that many of the methods used in Optimi are available as part of the low energy framework. The emphasis is set on use case analysis to encourage developers to optimize according to specific case. And using the gap sensors may be characterized as services defined for generic applicability. However, there's no approach of streaming, and there's no consideration of firmware update wirelessly. So the areas requiring most attention following our work in Optimi are the following. Battery weakening occurs after repeated charge. We believe this is because of the way simple battery charging chips that we use did not optimize the battery charge and recharge according to specific use pattern. We hope to integrate battery charging into the energy-aware paradigm, and RF communication was often broken due to heavy Wi-Fi interference. This resulted in poor performance and retries that used a lot of battery energy. As the density of Wi-Fi hotspots increased, perhaps frequency hopping is not the only solution. A low-energy method could be developed where the home PC predicts clean radio bands and tells the sensors which to use more of, for example, may be more profitable than using random hopping. In reality, we found Wi-Fi hopping is rather cyclic and not so random, such that a human could predict the corruption cycle time. Et voilà.
this nice talk. I'm really sorry because we are out of time. So maybe questions will be during the lunch. Okay. Thank you very much. And we can continue with the next session, that is